Good evening. This is Math 2414, Calculus 2. It's February the 26th. So just wanted to make a few announcements, and then we'll get started with the material today. The February 25th homework, the homework that was due yesterday, I've posted the grades there. So you can look at your D2L gradebook for those grades. Remember that I also post the solutions to those problems, and those are where I have syllabi and other documents on my Google site. So if you look at this, you can always find the solutions to the homework problems in the section that says syllabi and other documents. And I have that those solutions on there by date. Also, let me point out that if your homework grade maybe is not as high as you thought it was going to be when you turned it in, don't forget that if you do not include your work, or if there's a big gap and I don't see work that would be required to go from one step to the other, a substantial amount of work especially, then you're going to get penalized for that. So just keep that in mind, that I do want to see everything. I want to see all your work when you turn that homework in. Most of you are doing a pretty good job with that, so that's okay. But occasionally it might be a little bit of an issue. Online office hours, haven't reminded you of that in a while, but don't forget that I do have online office hours Tuesday, Wednesday, Thursday from 11 to noon, and then Sunday and Tuesday evening from 8:30 to 9:30. For example, last night I had someone from a college algebra class get online at 8:30 when I opened up my WebEx room last night, and she asked a few questions, and she got some good homework questions answered for about 20-25 minutes yesterday. So it's a good opportunity to get some questions answered. The Exam 2 review will go up next week. So it'll be posted next week sometime. That's the week before spring break. So we have 2 weeks of classes left. So we have lecture twice this week, lecture twice next week. Sometime towards the end of next week, I'll post the review for Exam 2. And then you will have 2 weeks before Exam 2 comes along, because remember, we have spring break after next week. So that's a good thing. That's certainly something to be shooting for, is spring break, because it gives us a nice bit of a break to maybe get caught up on things and get prepared for Exam 2. So that's something to be looking forward to, definitely. All right, so today remember what we're doing is we're kind of going through and looking at integration in the chapter that we're currently working in, and looking at different techniques for integration. So we've been looking at integrals, basically. And so our last goal in this chapter, is to look at a type of integral called an improper integral. That's a special type of integral, and you need, as calculus students, to be able to evaluate an improper integral, and certainly pick an improper integral out from the crowd. In other words, be able to identify in a group of integrals which ones are improper integrals and which ones are just proper integrals, right? Typical integrals. And then not only do you have to be able to pick them out of the crowd, but you have to understand the geometry behind an improper integral, and then understand how to evaluate an improper integral. All right, but in order to do that, there are some things we have to be able to do with limits. But believe it or not, this involves limits in a limiting process. And so we will need to take a little bit of a step back in order to be able to do improper integrals. We'll need to be able to go back and look at certain types of limits before we do anything else. All right, so let's get started on this. What I want to do is I want to start off with an example that is an integral. And I want to talk about this integral a little bit. And it's a definite integral from -1 to 1 of 1 over x squared dx. Now this is a pretty easy function as far as finding the antiderivative, because this is just x to the -2. So this is the integral from -1 to 1 of x to the -2 dx. So using the power rule, right, this is just a power rule problem as far as the antiderivative goes. You end up with the negative of x to the -1. So you end up with -1 over x, and that goes from -1 to 1. All right, and then using the fundamental theorem, the upper limit, you'd get negative 1 over 1. And then you subtract the lower limit. And you have to kind of be careful here. This is going to be the negative of 1 over negative 1. You have all sorts of negative signs wandering around in this problem. So that gives you negative 1. And be careful, you know, these two negatives right here give you a positive. And so you end up with minus 1 right here. And you get negative 2. Now this all looks just fine, right? No problems at all. But there is one big problem, and that is everything I've just written is total garbage. Everything on here is totally wrong. This is all completely incorrect. So this entire problem is worked incorrectly. In fact, this is totally wrong. Because, gee, it started off like, hey, this is not going to be bad, right? This is a pretty simple integral. But everything's garbage here. Why is it garbage? So why is this all garbage? And so what I want you to do is think about the function and think about this geometrically. You know, you have 1 over x squared. The graph of 1 over x squared is this function that has a vertical asymptote on the y-axis. And so its graph looks something like this. Has symmetry with respect to the y-axis. And so what I want you to think about here is where do we integrate this function? Well, we integrated it from negative 1 to 1. And notice we integrated it across the discontinuity right there. There's a discontinuity, an infinite discontinuity on the y-axis, and we've integrated across that discontinuity. Think about this geometrically. What we just did is we're talking about the area of this region right here. And notice this is an infinite region right here. Right? So this is an infinite region. And if the area were to exist, and believe it or not, sometimes infinite regions like this have a finite area, even though the region is a infinite region, even though it might have an infinite perimeter, the area may in fact be finite. Strange, right? That could possibly be true, but definitely it's true here. And so if this area is finite, it sure as heck is not equal to negative 2. Right, but that's what we got when we evaluated this integral. We got negative 2 at the top there, not negative 12, negative 2. And so there's no way, if that area actually existed, that it could be negative 2, because first of all, you can't have a negative number for an area. This integral, this region's entirely above the x-axis, and so we should get a positive number for the integral. Right? There's all sorts of problems right here. Right? We do know that an integral of a nice normal, what I'd say, term a normal region that sits underneath the curve, right, f, we do know that that area is equal to the integral from a to b of f of x dx. But that function does not have any discontinuities between a and b. It's a continuous function. We just kind of accept that so far that these functions have been continuous. If you go back and look at the way the fundamental theorem of calculus is stated, it talks about the function in the interval being a continuous function. But here, all of a sudden, you've got this definite integral where we're integrating across a discontinuity. This type of integral, the integral from negative 1 to 1 of 1 over x squared dx, is called an improper integral. right, an improper integral because y equals 1 over x squared has an infinite discontinuity. In other words, a vertical asymptote, right, has a vertical asymptote between the two limits of integration. Now, all right, so that's what makes it an improper integral. Now, the main goal of our lecture today is not to talk about improper integrals, but I wanted to start off with an improper integral to start getting you some kind of an idea of what we're faced with here. In order to be able to evaluate this kind of integral, in fact, what we will need to be able to do is we will need to be able to evaluate certain types of integrals, certain types of limits called indeterminate forms. And in order to be able to tackle this kind of improper integral, we'll need to be able to deal with those kinds of limits. Well, we have a very limited tools at our disposal for evaluating indeterminate forms, and so that's what we need to do. We have talked about indeterminate forms in calculus. When you took Cal 1, you should have talked about indeterminate forms a little bit, but kind of limited probably in what you looked at. And so what we're going to do is we're going to turn our attention back to these indeterminate forms, rather, and be able to evaluate those, and then that, in fact, will allow us to deal with an improper integral. All right, so let me show you that y equals 1 over x squared has a vertical asymptote, in other words, an infinite discontinuity at x equals 0. So an integral like this, let's say the integral from 0 to 1 of 1 over x squared dx, this is improper because notice that the discontinuity is one of the limits of integration. The integral we just talked about, the integral from negative 1 to 1 of x squared dx, is improper because the infinite discontinuity is actually between the two limits of integration. But then notice that this integral from 1 to 2 of 1 over x squared dx, there's nothing wrong with that integral at all as far as it being proper or improper. That's not an improper integral, right? Because the infinite discontinuity is at 0, but we're integrating from 1 to 2. So this is just a typical old integral that we've seen before, right? So this one we know how to do. So we know how to do this. But this is the question: is how do we evaluate this type of integral? And so we are not ready to deal with that just yet. We will talk about that Wednesday, right? That's our goal for Wednesday, is to actually talk about improper integrals and how you actually evaluate them. What we need to be able to do first is we need a skill that we don't necessarily have yet. We need to be better at evaluating limits of indeterminate forms. Before we can tackle improper integrals. And that's what we want to talk about today. All right, that's our goal. All right, so indeterminate forms, that's what we're tackling right now. So, we've already kind of done some of this before. First of all, indeterminate forms are kind of in this form. I'm going to list some forms out. 0 over 0 is an indeterminate form. Positive or negative infinity over positive or negative infinity. is an indeterminate form. Now, you have to be careful when I write those kinds of statements out. We are not saying that an expression is 0 in the numerator and 0 in the denominator. We're saying really that the expression is getting close to 0 in the numerator and close to 0 in the denominator, right? So more properly, you might say the numerator is approaching 0, the denominator is approaching 0. Or you might say the numerator is approaching positive or negative infinity, and the denominator is approaching positive or negative infinity, right? That's really what we're saying when we write these indeterminate forms down. And so some other indeterminate forms, there's others besides these. 0 times infinity, a multiplication problem, is an indeterminate form. Infinity minus infinity is an indeterminate form. And then we have some exponential indeterminate forms. We have 1 to the infinity. That's an indeterminate form. Infinity to the 0 is indeterminate. And 0 to the 0 is indeterminate. Right? Those are exponential indeterminate forms. These are all forms that when an expression approaches one of these forms, you don't really know what's happening to the expression. All right, now some of these, in particular 0 over 0 and a little bit with infinity over infinity, you've probably dealt with already before. So for example, when I taught Cal 1 in the fall, we talked about some of these indeterminate forms. So as an example, something simple, if you have the limit as x approaches 3 of x minus 3 over x squared minus 9. Now recall that when you try to evaluate a limit algebraically, you try to use substitution, right, to evaluate the limit. In other words, you just substitute that 3 in. And remember, you have properties that guarantee that that would work, that substitution works when you have a function that's continuous, and then a couple of other restrictions and everything. So when a function is continuous, well, and actually that's actually the only real condition that you need, then you can do that. So when you try substitution here, what happens? In the numerator gets close to 0, doesn't it? Because when you substitute 3 in, you get 0 there. And the denominator gets close to 0. In other words, the limit as x approaches 3 of the numerator is 0, and the limit as x approaches 3 of the denominator is equal to 0. So this limit is 0 over 0. But in Cal 1, you saw that sometimes what you can do is you can eliminate the indeterminate form by going ahead and using some algebra. Like in this case, we could factor the x squared minus 9 and get x plus 3 times x minus 3. And then notice the x minus 3's divide out, and that's legal to do because you are changing the domain of the function, but only at 3. But that doesn't matter when you have a limit as x approaches 3, because the limit as x approaches 3, you don't really care what's happening necessarily at x equals 3. So changing the domain at 3 by scratching those x minus 3's out is actually okay to do. There's nothing wrong. It doesn't change the value of the limit. And sure enough, we can now evaluate this using substitution, and we get 1 over 6, right? Just substituting 3 in for x. And so 1/6 is the limit as x approaches 3 here. So even though the numerator is getting close to 0 and the denominator is getting close to 0, the fraction itself, the ratio of those two quantities, is approaching 1/6. You could certainly look at this on a graph, and you could see that the graph is approaching 1/6 as x is approaching 3. So that would, even though the function itself is not defined at 3, if you're on either side of 3 and getting close to 3 with an x value, you're certainly going to see that the y value is getting close to 1/6. All right, so that seems okay, right? We had an indeterminate form. We used just canceling out common factors there. We used some algebra there, and we got rid of the indeterminate form. And all of a sudden, we could evaluate using substitution. Right? A limit like this one, the limit as x goes to infinity of 4x cubed minus 1 over 5x cubed minus 1. See what happens here? You get the limit of the numerator as x goes to infinity, as x gets large, is just infinity, right? And the limit as x approaches infinity of the denominator is also infinity. And so notice this is the indeterminate form infinity over infinity. So this is indeterminate right here. In other words, just because a fraction's approaching infinity over infinity, you don't necessarily know based on that form what's happening to the fraction. This is also a problem where there was actually a couple of ways you could have figured out this limit. One way, the way I frequently talk about this, is I look at the dominating terms in the numerator and the denominator. And if you look at the dominating terms, right, remember the terms with the biggest powers are the dominating terms. In other words, they control what's happening to the expression as x goes to infinity. This is only true when you have a limit as x goes to infinity or negative infinity. But the dominating terms here are 4x cubed and 5x cubed. So this fraction just gets closer and closer to 4x cubed over 5x cubed as x gets large. And notice the x cubes divide out and you get 4/5, and boom, you've evaluated the limit there, right? That the limit of that expression as x gets large is 4/5. But the y values are getting closer and closer to 4/5 as x gets larger and larger. Now there's also, if you remember, you might have not looked at it that way. You might have looked at it a different way. Another algebraic trick here to evaluating this limit is to multiply the numerator and denominator by 1 over x cubed, the largest power in there. In other words, divide all the terms by x cubed. And when you do that, you get the limit as x goes to infinity of 4 minus 1 over x cubed over 5 minus 1 over x cubed. And notice what happens there is that those 1 over x cubes, those go to 0 as x gets large, right? As x gets large, 1 over a big number is going to go closer and closer to 0 like that. And sure enough, what happens there, you are left with 4/5, right? And so either way, you know, we get that same value there. So two different ways to evaluate that limit. So what you might say right now is, well, wait a minute, I seem to know how to evaluate indeterminate forms. This shouldn't be too big a deal. I shouldn't have a problem with this at all. The only problem is that these little algebraic tricks that we've talked about in these two problems don't always bail us out of an indeterminate form. So for example, if we looked at this limit right here, very simple problem. The limit as x goes to 0 of sine x over x, which you probably have talked about this limit. You should have talked about this limit in Cal 1. Well, that's an indeterminate form, right? When you try substitution, you get 0 over 0, right? In the numerator, the limit as x goes to 0 of sine x, using substitution is 0. And in the denominator, the limit as x goes to 0 of just x, well, that's also 0 using substitution. So this is an indeterminate form, 0 over 0. But see, there's no algebra you can use to evaluate this limit. So back in Cal 1, you might have used either the graph to evaluate this limit, or you might have made a table of values to evaluate the limit, or you might have used a kind of complicated geometric argument to evaluate this limit. But there's no simple algebraic way to deal with this, right? So algebra does not bail us out of this problem. So algebra does not bail us out on this indeterminate form. Okay, so if we looked at this problem, the limit as x goes to 0 of e to the 2x minus 1 over x, well, sure enough, if you try to use substitution there, once again, you get 0 over 0, right? The limit of the numerator is, when you use substitution, just gives you 1 minus 1 or 0. And certainly the limit of the denominator is 0 as x goes to 0. So this is indeterminate, but it's exactly like the problem before. Algebra is just not going to bail us out of either one of these examples. Right? And so we've got to come up with different strategies for evaluating an indeterminate form, right? That's going to work in a more general context. All right, so to evaluate some indeterminate forms, again, this will not always work, but this is going to give us a whole another strategy for evaluating indeterminate forms. So to evaluate some indeterminate forms, we can use what is called L'Hopital's rule. And you'll see L'Hopital, that person's name spelled several different ways, by the way. That's my traditional spelling there, is to use this rule. And some of you who are watching this recorded video, this recorded lecture, may have already talked about L'Hopital's rule somewhere. I am going to kind of assume that you have not talked about it yet, right? So if you have, that's great, but if you haven't, I'm definitely going to want to go back over this again. You definitely, as a Cal 2 student, need to know about L'Hopital's rule. All right, so what you do is you assume, this is the rule, assume C is in the open interval from A to B. So C is somewhere inside that open interval. And then you also assume that f and g, two functions, f and g, are differentiable in the open interval from A to B. And you also assume that g prime of x is not equal to 0 right, so that the derivative is not equal to 0 for all x in the interval from A to B, whatever this interval is, except maybe at C. At x equals c. And remember, c is some value in between a and b. And then what you have is this rule right here. If the limit as x approaches c, right, that's where we're taking the limit, is at c, of the quotient f of x divided by g of x, if that is equal to 0 over 0 or positive or negative infinity over positive or negative infinity. Right, it's equal to one of those two indeterminate forms. Then, and here's finally the punchline, then the limit as x approaches c of f of x divided by g of x is equal to the limit as x approaches c of f prime of x divided by g prime of x, as long as this limit exists. Right. This is also true. The L'Hopital's rule also is true for the limit as x approaches plus or minus infinity of f of x over g of x. In other words, it doesn't have to be the limit as x is going to some finite value. It can be an infinite limit or a limit at infinity as well. And as long as you get one of those two indeterminate forms, then the limit of the ratio of the two functions is got to be equal to the limit of the ratio of the derivatives of the two functions, as long as that second limit exists. Okay? Now, so that's L'Hopital's rule. Now, it seems like it's kind of restrictive as far as all the different assumptions at the beginning, but it's really not, because most functions that we're going to deal with would satisfy those conditions. So it's really not too restrictive of assumptions that you're making at the beginning. All right, so now why might this rule actually work? or actually be true. Now I'm going to kind of sketch through just a brief look at what's going on here. This is not a proof right here at all, so make sure that you understand that. So, but this is definitely just kind of sketching through why it might be reasonable that this is true. So if we look at the limit as x approaches a of f of x, and we get that that's 0, and the limit as x approaches a of g of x, and we have that that's equal to 0, right? And we know that g prime of a is not equal to 0 for x near a, right? That's what we were talking about with those assumptions, right? Well, we have what are called, if you remember back from Cal 1, we have what are called the tangent line approximations to functions. Now, the tangent line approximations sounds like a fancy term there, but remember, the tangent line approximations are simply the equations of the tangent lines. All right, and so the tangent line approximations for f near, so you're talking about the points a, f of a, right? And you're also talking about the point a, g of a. And what do we have here? The tangent line approximation, all it is the point slope form. So don't make this any like something that's really mysterious. This is just the point slope form. Remember the point slope form, I'll write this over here, for a line is simply y minus y1 equals m times x minus x1. And if you add the y1 to both sides, it's just y1 plus m times x minus x1. Right? x1 and y1 is a point on the graph, and m is the slope. So the tangent line approximation around the point a, f of a for the function f is simply this function right here, that we're saying that f of x is approximately this line right here, f of a plus f prime of a times x minus a. Right? Remember, f prime of a is just the slope of the line. It's the slope of the tangent line there. And g of x, its tangent line approximation would be g of a plus g prime of a times x minus a. Again, don't freak out on those two forms right there. Those are simply the point slope form right here. And I just added the y value to both sides of that equation. Right? So this is y1 right here plus m times x minus x1. That's all it is. It's just the point slope form is all it is. Okay? And so we're saying that those two equations right there approximate the curves f and g through these points a, f of a, and a, g of a. So now what does that give us then? If you look at the ratio f of x over g of x, remember that's the what we're after when we're talking about L'Hopital's rule, are these fractions like this, then that would be approximately equal to f of a plus f prime of a times x minus a over g of a plus g prime of a times x minus a. All right, it's just the ratio of those two tangent line approximations. And so now what have we got here? Well, if we've got the limit as x approaches a of f of x over g of x, then that it's reasonable that that would be the limit as x approaches a of f of a plus f prime of a times x minus a, and then g of a plus g prime of a times x minus a. But, you know, these functions are continuous, and so what are we saying here? When we're saying that the limit as x approaches a of f of x is equal to 0, we're really saying that f of a is equal to 0. And same thing with this limit. If we're saying that the limit as x approaches a of g of x is equal to 0, right, this function is going to be a continuous function, so it would have to be the case that g of a is equal to 0. And so what do you have here? That sure enough, there's f of a and g of a in this fraction. And so you have that this has got to be equal to the limit as x approaches a of f prime of a times x minus a over g prime of a times x minus a. And then what happens? The x minus a's divide out. And so you get that this is the limit as x approaches a of f prime of a divided by g prime of a, like that. Right, and so what do we have here? We have that with these restrictions in place that we've talked about, that the limit as x approaches a of f of x over g of x would be the same as the limit as x approaches a of f prime of a over g prime of a. What had to be true in this problem is these two limits certainly had to be true, right? That the limit of the ratio, the limit of the fraction had to be the form 0 over 0, right? And because we needed these two terms in here to go away in order for this little calculation to work out, right? So that the x minus a's could divide out, and we just have f prime of a over g prime of a. Now, this is definitely not a formal proof for L'Hopital's rule, but it does give you a good idea that it would be a true statement, that L'Hopital's rule actually does work, so to speak, all right? So, and now what we're going to do is we're going to start looking at some L'Hopital's rule problems and kind of tackling the ins and outs of this. First of all, let's look at the problem that we talked about a few minutes ago. There's actually two problems we talked about a few minutes ago that were problems that we could use algebra on to evaluate the indeterminate form. So now let's use L'Hopital's rule instead. So this was the first problem I had. It's the limit as x approaches 3 of x minus 3 over x squared minus 9. Now, I will want you to do this. I will want you to identify the indeterminate form. Always identify the indeterminate form. I will be looking for that on a test and on homework. All right, so make sure that you always do that. You say, okay, this is going to be 0 over 0. Now, we saw, if you remember a little while ago, that this limit was 1/6, but now we've got that L'Hopital's rule says that this limit should be equal to the limit as x approaches 3 of the derivative of the numerator, which is 1, over the derivative of the denominator, which is 2x. Note that L'Hopital's rule does not say use the quotient rule here. It says take the derivative of the numerator and the denominator separately. So that's what I did here. And does that limit exist? Well, sure enough, it does using substitution. And what do? You get 1/6. Wow, that was actually much simpler even than what we did a few minutes ago. All right, another problem we did a few minutes ago is we did this limit, the limit as x approaches infinity of 4x cubed minus 1 over 5x cubed minus 1. And we saw that that limit was equal to 4/5. Well, this is the indeterminate form infinity over infinity, and so we can use L'Hopital's rule. And so when I use L'Hopital's rule, then this limit should be equal to 12x squared over 15x squared, right? The derivative of the numerator over the derivative of the denominator. And sure enough, what happens there, you could divide out the x squares now, and you've got 12/15. That this is just the limit of a constant, right? 12/15. And what is 12/15 reduced down to? It reduces down to 4/5. Right, so this limit's got to be 4/5, which is what we saw a few minutes ago. And so certainly L'Hopital's rule works really nicely on problems like that, because it's a quick way to get through the limit. And remember, what we're saying is, if this last limit exists, which it does, it's equal to 4/5, then the original function, the original limit must also be equal to 4/5, right? That's what we're saying here. Same thing in the previous problem, that last limit was equal to 1/6, and since it existed, that means the original limit had to be equal to 1/6 also. All right, so let's look at some more problems here, because there's definitely some issues even with L'Hopital's rule, because it all looks really nice and simple here, but that unfortunately is not always the case. All right, so here I've got the limit as x goes to 1 of the natural log of x cubed over x squared minus 1. Now, what you might do here, before you even think about L'Hopital's rule, is you might first bring the 3 down in front in the logarithm, just using the power rule for logarithms. And then please use substitution. Don't just dive into L'Hopital's rule and automatically assume that you're going to use it, because that's not true. You have to make sure that you actually have an indeterminate form where L'Hopital's rule is appropriate. So you have to use substitution. Always substitute first and verify you have 0 over 0 or plus or minus infinity over plus or minus infinity. Right? Verify that you can actually use L'Hopital's rule in the problem. The problem, it will be incorrect, almost certainly be wrong. You'll get the wrong answer if you try to use L'Hopital's rule on a form that is not one of these two. All right, so you got to be really careful there. Use substitution first and verify you have one of these indeterminate forms. So in this problem, sure enough, I get the natural log of 1 in the numerator, which is 0. Don't forget that the natural log of 1 is 0. So in the numerator, I do get 0. In the denominator, I certainly get 0. And so now I'm okay. Now I can use L'Hopital's rule. So now use L'Hopital's rule. And so when you use that rule, you get the limit as x goes to 1. In the numerator, you get 3 times 1 over x. And in the denominator, you get 2x. Now go ahead and simplify that first algebraically before you do anything else. So when you simplify that algebraically, you've got 3 over x over 2x. And so that would be the limit as x goes to 1 of 3 over 2x squared. And see, sure enough, now that's an easy limit to evaluate using substitution, and you get 3/2. And so that would be the value of this limit. Now, it's 3/2. So since that's the value of that last limit, it's got to be the value of the original limit, also using L'Hopital's rule. Now, don't forget that you can certainly check this out graphically. And I think sometimes students kind of forget that they can do this, but you could check this problem out graphically and make sure that this limit's actually 3/2. See, so look, if you go ahead and sketch the graph. So let me go ahead and sketch the graph of this function. Let me clear out a function I was looking at in college algebra. And so I'm looking at, let's say, 3 natural log of x in the numerator. So 3 natural log of x, close the parentheses there, close the parentheses, and then divided by x squared minus 1. Make sure I put parentheses around the denominator also. I get x squared minus 1, close the parentheses there. Right, when I look at this function, remember, we're looking at the limit as x goes to 1. And sure enough, what happens here is the limit as x goes to 1. If you look at this, what are you getting here? Now the graph doesn't show a discontinuity, but there's actually a discontinuity there. And so I'm going to take a picture of this, save it to my photo library, and then I'm going to come back to my worksheet here, and then I'm going to actually pull out this particular graph right here, very last one we've done. Okay, so we were taking the limit as x approaches 1. Now this function, and remember the function is f of x equals 3 natural log of x over x squared minus 1. Right, that's the function. And notice that f of 1 does not exist. Right, f of 1 gives you 0 over 0. Right, so technically, not technically, but definitely what happens, there's a hole in the graph right there at that point where an x is equal to 1. But the limit, when we're talking about the limit of this function, as x approaches 1, we don't care what's happening at x equals 1. We just care about what's happening close to 1. And what happens when you're close to 1 on this problem? Right, when I'm close to 1, right, you come over here, and what are you going to get? You're going to get that regardless of which side of 1 you're on right here, you're going to get y values that are around, and sure enough, what is it? Around 1.5, around 3/2. Right, that's what we're talking about. So even though this function doesn't exist, there's a hole in the graph there. The limit as x approaches 1 definitely exists. And you can tell graphically that sure enough, the limit should be equal to 3/2. All right, so please don't forget you can do that. All right, so let's look at another limit here. The limit as x goes to 0 of sine of ax divided by sine of bx. All right, if you try substitution, remember that should be your first line of defense. Always try substitution first. So using substitution, what do you get? Right, when you substitute 0 in the numerator, you get sine of 0 over cosine of 0 when you try substitution, and sure enough, you get 0 over 0. All right, so this is a problem that is a L'Hopital's rule problem. So we use L'Hopital's rule. And when you use that rule, what happens? You take the derivative of the numerator, and the derivative of the numerator would be a cosine of ax. And the derivative of the denominator would be b cosine of bx. Right, and now you try substitution again, but the cosine of 0, right, which you get in both the numerator and the denominator, is 1, remember. And so this is just a over b. And so sure enough, we've evaluated the limit, right? We get that last limit has a value of a over b, so the original limit had to have a value of a over b also. All right, so now this can get to be a little bit more complicated the further along we go with this. So, so let's look at a few more problems here. And as we go into this, you're going to find that it's going to get more involved as we go through. And there's going to be some situations that are going to be kind of unexpected here as we go through this. All right, the next problem here, the limit as x goes to 0 of the square root of 25 minus x squared minus 5, all divided by x. And sure enough, what happens here, when you take the limit as x goes to 0 of that numerator, in other words, when you use substitution, you get that numerator's limit is 0. And then certainly the denominator's limit is 0 also. And so this does go to the indeterminate form 0 over 0. So we use L'Hopital's rule. And so let's see what we get here. We get the limit as x goes to 0. The denominator is easy. That's just 1. The numerator, though, is the chain rule for differentiation. And so you'd have 1/2 times 25 minus x squared to the negative 1/2. That's the derivative of the outside function, times the derivative of the inside function, which is negative 2x. Yuck. The minus 5, its derivative is 0. So what happens, the 2's divide out, and you get the limit as x goes to 0 of x over the square root of 25 minus x squared. And see, now I can use substitution. And in the numerator, I get 0, and in the denominator, I get 5. I don't get 0 in the denominator, I get 5. And so that's 0. So the value of that limit would be, the limit at the end of the problem would be 0, And so that would be the limit for the original problem also. That would be 0 as well. All right, so now, next problem. It's going to start getting some trickier problems here. The next one is the limit as x goes to infinity of x over x squared plus 1 to the 1/2. So remember, L'Hopital's rule does work for limits at infinity also, if you have the right indeterminate form. But if x is getting large, what I want you to notice is that certainly the numerator gets large, right? The limit as x goes to infinity of x is certainly infinity. And in the denominator, the limit as x goes to infinity of x squared plus 1 to the 1/2, well, that's also infinity, right? As x gets larger and larger, that would get larger and larger also. So this is infinity over infinity. And so this is a problem where maybe L'Hopital's rule works here. All right, so use L'Hopital's rule. Write that out. And so you get the limit as x goes to infinity of 1 in the numerator, and then in the denominator I get 1/2 times x squared plus 1 to the negative 1/2 times 2x. Now watch what happens. The 2's divide out in the denominator there, and so I have the limit as x goes to infinity of 1 over x squared plus 1 to the negative 1/2 times x. And so you get rid of the negative exponent there, right? And when you get rid of the negative exponent, this is kind of a problem here, because what's going to happen, you've got x squared plus 1 to the 1/2 in the numerator now over x. And I want you to compare the original problem and this new limit right here. And notice we have not helped ourselves at all. All I've done is flip the fraction over. So yeah, the second limit is also indeterminate. We could use L'Hopital's rule again, but all that's going to do is take us back to the original problem. It's just going to cycle back and forth between these two limits. And so L'Hopital's rule will not work on this particular indeterminate form. So L'Hopital's rule does not work here, because you just flip-flop back and forth between those two limits as you continue to use L'Hopital's rule. So instead you have to use, in this case, some algebra from back in Cal 1 that would allow you to deal with this kind of a problem. And remember, one way to deal with this, I don't know if you remember this or not, but is to multiply the top and the bottom by 1 over x. And when you do that here, so this is just algebra, no L'Hopital's rule here at all. In the numerator you have 1, and in the denominator, you've got the square root of x squared plus 1 all over x. And so what you do, it's kind of an algebraic trick here. You take the denominator and you rewrite this as the square root of x squared plus 1 over the square root of x squared, right? You take x, that x right there, and you rewrite it as the square root of x squared. As long as x is positive, which x has got to be positive for this limit, that's okay to do. And so then what happens here is you get the limit as x goes to infinity of 1 over, see, and now you can divide those two radicals. And so certainly what happens here is you have 1 over the square root of 1 plus 1 over x squared. That's why you wrote that x is the square root of x squared, so you could divide the two radicals out. And then notice as x gets large, this fraction right here, 1 over x squared, well, that's now going to go to 0, because you've just got 1 divided by something that's getting bigger and bigger and bigger. That's going to go to 0. All right, so what do you end up with? You end up with 1 here you end up with 1 over 1 or 1. All right, so this is a problem that was kind of unexpected. So now let's look at some problems where the indeterminate forms are a little bit different in how we might approach these forms. All right, so now let's look at a problem where the indeterminate form is not quite the same as what we've been talking about. So let's say we have the limit as x goes to 0 from the right of x cubed times cotangent x. So you have the limit of a multiplication problem right here. And so the limit, if you think about this, the limit as x goes to 0 from the right of x cubed is just 0 by substitution. And the limit as x goes to 0 from the right of cotangent x, using substitution, right, the cotangent of 0, right, as you're going from the right side, is actually positive infinity. Right, if you think about the graph of the cotangent function, in case you have forgotten, and you know, it may have been a while since you've dealt with the cotangent function, but cotangent kind of looks like this, right? And it has vertical asymptotes at x equals 0 and x equals pi. And so what happens as you approach 0 from the right side of 0? Well, the graph, sure enough, is getting big, right, like that, as you're approaching 0 from the right side. So what happens here? This limit is 0 times infinity. That's the form. And that is an indeterminate form. The first factor is trying to make the expression equal to 0. The second factor is trying to make it big without bound there. And so it's kind of this tug of war between these two factors and who wins, right? First factor wants to make it 0. Second factor wants to make it big. But it's not a problem where I can use L'Hopital's rule, because L'Hopital's rule only works on 0 over 0 or infinity over infinity. So what you try to do is use some algebra and try to write it so that you can use L'Hopital's rule. So for example, in our problem, instead of putting cotangent in the numerator, I could put tangent in the denominator. And that's the same function, right? And now what happens? Well, the numerator is 0 still, but now the limit of the denominator, the limit as x goes to 0 of tangent x, is also 0. And so now I can use L'Hopital's rule. So the moral to the story here is that even though you have an indeterminate form, you can't use L'Hopital's rule until you rewrite it so that it's either 0 over 0 or infinity over infinity. So that's what I've got now, 0 over 0. Now I can use the rule. And so I've got the limit as x goes to 0 from the right of 3x squared over secant squared x, right? That's the derivative of tangent. And sure enough, what happens when I try substituting 0 over or 0 in the numerator and the denominator, I now get 0 over 1, and you get 0 right away. So the limit of the last limit's equal to 0, so that means the original limit has to be equal to 0 also. All right, so that was a different indeterminate form that we started off with. Next problem, we have the limit as x goes to 0 from the right of 10 over x minus 3 over x squared. All right, so once again, don't forget here from limits, some stuff from blast from the past on limits. But if you have the limit as x goes to 0 of some function approaches a constant over 0, like that, a non-zero constant, I should say, in particular, right, where k is not equal to 0. So if the numerator is going to some constant, the denominator is going to 0, well, that goes to infinity, plus or minus infinity. Depends on the situation. So in fact, that's what's happening in this particular limit here. When you try to evaluate this, you get 10 over infinity and 3 over infinity here. And so this ends up going to infinity minus infinity. And that's indeterminate. It's not 0. It could be 0 at the end. We don't know from the form, though. Infinity is not a number, so it's not like you can take infinity and subtract infinity and get 0. That may not, in fact, be the case. So once again, what do you try to do? You use some algebra to rewrite this expression. So in this case, just get a common denominator. So that's just 10x minus 3 over x squared. And see, now, what do you get? You actually don't have an indeterminate form anymore. You get that this is negative 3 in the numerator. As soon as you see negative 3 in the numerator, that blows it as far as L'Hopital's rule goes, right? And 0 in the denominator. So it's not indeterminate. Instead, what do you get there? The numerator is positive, the denominator is negative, and you're getting a constant over 0. This is now negative infinity. All right, so this is a case where infinity minus infinity is just negative infinity, which means that the subtraction problem gets to be a bigger and bigger negative number, which means the second fraction gets to be a lot bigger than the first fraction. And if you think about it, x squared is going to get big faster than x is in the original fractions, and so that makes sense here. All right, next problem. What I want to look at here is I want to look at the limit as x goes to infinity of e to the x over x squared. And in particular, I want to compare, I'm going to use this limit here, to compare growth rates for e to the x and x squared. And I say growth rates, but really relative growth rates. In other words, which one grows faster? Well, the limit as x goes to infinity here, the numerator certainly goes to infinity, and the denominator does. So this is a L'Hopital's rule problem. And so you get the limit as x goes to infinity. Well, the numerator is still just e to the x, but the denominator is 2x. This is still infinity over infinity. So I use L'Hopital's rule again. And I get the limit as x goes to infinity of e to the x still in the numerator over 2. And what is this approach, though? Well, this approach is infinity over 2. That's just infinity, right? You take a number that's getting large without bound and you divide it by 2, and it's still a number getting big without bound. And so what have we got here? That the fraction at the beginning, e to the x over x squared, as x gets large, is actually just going to infinity. And so what that implies is the numerator is bigger than the denominator. The numerator is much bigger than the denominator. The numerator, in fact, is growing much faster than the denominator. And so what are we saying here? E to the x grows faster than x squared. Right? And yeah, these kinds of limits like this are really useful for comparing growth rates of different kinds of functions. All right, we have one last problem that we're going to look at here before we close this down for the night. Now let's say we have the limit as x goes to infinity of 1 plus x to the 1 over x. Now, if you look at the little pieces in there, the limit as x goes to infinity of 1 plus x, if x is getting large, well, that just goes to infinity. And the limit as x goes to infinity of the other little piece, the exponent, you get 1 over x, that's 1 over infinity, 1 over a number getting larger and larger. That goes to 0. And so this form right here is going to be infinity to the 0. And that is indeterminate. You're taking a number that's where the base is getting bigger and bigger without bound, but the exponent's getting closer and closer to 0. So what happens, it's like, again, it's a little tug of war here where the base wants to make the expression bigger and the exponent wants to make the expression equal to 1. Right? And so they're competing with each other. Who wins in this case? And this is a tough limit. This kind of limit is a tough one sometimes to evaluate using L'Hopital's rule, but it can be done. There's a trick to this, though. What you have to do is let y equal the limit, or whatever letter you want to use. So let y be this limit. The nice thing about that is it gives you a nice little equation, and then what you do is you take the logarithm, the natural log of both sides of this limit, of this equation. And then you kind of bring up what might be sort of what seems like a little bit of a sleight of hand or a little bit of a trick here, but it's not. The idea is that since the logarithm is a continuous function, the natural log of the limit and the limit of the natural log are actually the same thing. That's actually a property you probably stated in Cal 1. So you interchange that limit and that logarithm like that. That's true. And then you use the power rule for logarithms and bring that 1 over x down in front. And then the idea here is to try to write this limit as a limit where you can use L'Hopital's rule. And this is actually not hard to do here because all you have to do is rewrite this as the natural log of 1 plus x over x. And sure enough, that limit, you have the natural log of something getting large in the numerator, that's just infinity. And in the denominator, that's infinity. And so this limit does go to infinity over infinity. And now I can use L'Hopital's rule. And so you get the limit as x goes to infinity. In the denominator, that's nice, that's just 1. In the numerator, the derivative of the natural log of 1 plus x is 1 over 1 plus x. So you have the natural log of y is equal to the limit as x goes to infinity of 1 over 1 plus x. And that just goes to 1 over infinity. That's 0 right there. Now you got to be careful here. Don't say that the answer is 0 here. Remember what you have. Don't forget the original statement was that y was equal to our limit. So what have I got here? I've got that the natural log of y is equal to 0, right? Using some algebra and L'Hopital's rule, I get that the natural log of y is equal to 0. And that tells me that y has got to be e to the 0 or 1. And so the value of this limit is equal to 1 right here. Very common to see students kind of forget to deal with the natural log of y. And you may have wondered why I kept on writing the natural log of y down every step. It's because students are always forgetting that this is not, the limit we're trying to evaluate is equal to y. But at the end of the problem, what do you get? You get the natural log of y is equal to 0. You've got to solve for y. And I get that y is equal to 1 down here at the end. All right, also not a bad idea, sometimes is to look at a graph like this and see if the graph does what you expect it to do, right? We're getting that this limit at the very top of the page now, we're getting that this limit's equal to 1, right, from below here. So what we could do is we could graph the function 1 plus x to the 1 over x, and we could actually see as x is getting large, does this function get closer and closer to 1? Right, so look at the graph right here. All right, so let's get rid of this graph right here. I'm going to clear that one out. And so the function I want to graph is 1 plus x, close parentheses, raised to the 1 over x power, close the parentheses there. Here's my graph. You know, that's what the graph looks like right there. But what are we interested in? We're interested in what happens to this graph as x gets to be larger and larger. So look what happens as we scroll down. Notice as x gets to be larger and larger, look at the graph. Sure enough, it's getting closer and closer and closer and closer to 1. Right? You can see how the graph has this horizontal asymptote at y equals 1. And so we have kind of got a good little graphical representation that this has actually got to be true. Right? And so let's see, I'm going to go ahead and kind of look at it this way and kind of scrunch up the scale a little bit. I'm going to take a picture of this so that this ends up in the notes. Also, I'd like this to be in the notes. So we go to the next page, going to take that graph out. All right, so this is the graph of our function. And what happens, you've got that this graph is approaching this horizontal asymptote at y equals 1 as x is getting larger and larger and larger, right? So as x gets bigger, as x goes to infinity, remember that means you're moving down in this direction in the x-axis. And what's happening? The y values certainly are getting closer and closer to 1 in this problem. There's this horizontal asymptote at y equals 1. Right? So we have nice little graphical evidence that this is going to be true. All right, so now what I want to do here is talk about your homework. Now remember that what I've done is I've taken the L'Hopital's rule section from the Cal 1 book, right? So the L'Hopital's rule section from the OpenStax Cal 1 book is section 4.8 from that book. And I have uploaded that section, and it can be found in the section on my Google site, Syllabi and Other Documents. Right, and so what I want you to do is for homework, textbook homework, first of all, let's see, so textbook homework. This is on page 470 from that book that part of the book that I've uploaded. I would certainly like you to do numbers 357 through 395, or actually 399. Those would all be problems that would be to look at. And then to turn in on March the 4th, I'm going to give you 3 problems off of that. And these should go relatively quickly. There's not anything too terrible here, but problems 368, 380, and 386. Actually, not 386, 384, I'm sorry. I'm going to do it that way. Yeah, 384. All right, so those 3 problems are to be turned in on March the 4th. I'm also going to assign some stuff, a problem or 2 on Wednesday as well. So you have 3 problems out of this section. Remember, this section's from your OpenStax book, and it's in Syllabi and Other Documents. So that's where you find it on my Google site. Okay? All right, so thank you very much for watching the video, for watching the recorded lecture. Please come by if you have questions. Otherwise, have a great day, great evening, and I will see you soon. Good night.